pages to pull instructions out of than you would be to reference data that the code was referring to. That may be the reasoning behind that. Who knows? May also just be some practical fabrication constraint on the size or something and worked out that way. Who knows? But in any event, they're not quite the same size. And then the L2 is significantly bigger. But if you look at these number of entries, right, you see we have 64 total entries here. Well, here you got 32K, right? So a lot of entries over here. So we don't really need that many entries to be cached up in the TLB because these are associations between a virtual page number and its corresponding physical page number. So there's not going to be just loads of different ones at any given point in time as your program is executing. If it exhibits any kind of temporal and spatial locality at all, these ought to be relatively few different sorts of pages out of your virtual address space that you would be roaming around in that would need to be cached up, right, for your program to run efficiently. So they're not near as big as these data caches over there, right? So the L2 is shown interacting with the memory controller for it shows a DDR3 here. It could be a DDR4 and a more recent processor. And that's the RAM, right? And that's interacting with the L3 cache. So when we're moving things up in the data cache, that's that line there. And the page tables that live in the memory, this RAM here, right? When we're touching those page tables to get the association of a virtual page number to a physical page number, those are the things that are being cached up in this translation look-aside buffer. Those entries out of the page table are being cached up into the translation look-aside buffer so that we'll have them and we won't have to go back to memory to get them as we refer to that same virtual page as we are executing the process, right? So we'll hit over and over in the TLB. So this should give you some view as to when we first looked at virtual memory and we said, oh, well, we're going to translate these virtual page numbers to physical page numbers. We have to go to the memory where the page table lives to get that information. And we were going, oh my goodness, this is virtual memory stuff is going to make the computer run really, really slow because it's forcing us to touch memory over and over again, just to resolve these virtual addresses to physical addresses. And at first it might look like that, but then we have all these reasons that we're learning now why that doesn't really work out that way in practice, that with the TLB and the fact that the page table references themselves are memory references that are subject to being cached up here, that we can not pay this huge price that it might at first look like multiple memory accesses. So in any event, they have this quick path interconnect that we haven't really talked about. It says you got 4 links, one of which goes to the RAM, right? That's how you get to the RAM from the processor to pull things in and either put them in the L3 or bubble them up into the DLB. That's and it says it can get 25.6 gigabytes per second is the bandwidth of each of these 4 connections. So that would show you how fast we can pull things out of memory into the caches ultimately. And why are these 4 connections? Well, remember we have 4 cores, so there's 3 other cores that each core is connected to. And if you recall when we discussed the cache coherence problem, where when one core would write into an entry in its cache and dirty it, it's different from when we brought it out of memory. Suppose the other cores had that entry in their caches. Well, they would have to have those entries invalidated now because the core has updated the contents of that memory location in his cache, right? So this is the cache coherence problem. It's these lines that you see going to all those other processors is where we have all those signals to do this cache coherent stuff to invalidate those entries and that the other cores might have that are the same as this core has. So if I write into the cache and the other guy has a copy in his copy has to get invalidated. That's where that valid bit that you saw in those caches would be getting turned off, right? Because of the cache coherence. And so those are the interconnects between the other CPUs to do that stuff. So any questions about how this thing is wired up and operating? So we have our review of our terms that we're using, the virtual memory size is N, the physical memory size is M, et cetera. And then we have the indices into the translation look-aside buffer cache and the indices into the physical cache and all these components of the different addresses, the virtual and the physical addresses. So let's look at the real computer and see what it picks out here. So we generate a virtual address, right? And you'll notice that the virtual address that we generate is 48 bits big. And you go, but wait a minute. I thought this was a 64-bit computer. What happened to the other 16 bits? Well, the truth of the matter is, although when you store a pointer into the memory of the computer, it takes up 8 bytes, full 64 bits, wired up on the CPU, we don't ever use the high order 16 bits. So it's kind of like, well, down the road, if we need it at some point as things evolve and we need this larger virtual address space, then we can accommodate with 48 bits. We're all ready to do it, because the registers are 16 or 64 bits wide and everything's all kind of set up for that. But for right now, we're really not using a full 64-bit virtual address space, only using a 48-bit virtual address space. But that's still some unbelievably humongous amount of memory. So it isn't really a, constraint on anything. And it will probably stay that way for a real long time. There probably won't be any need to really go to where we actually use those missing 64 bits on the left. So our virtual addresses in reality that are generated by the CPU, we have a 4K page size, which means we need 12 bits for the offset within that page. Select something out of 4K choices, you need 12 bits, right? So then all the bits that are left over, these 36 on the left, are the virtual page number. So that's the number of virtual pages that exist in our sort of mythical virtual address space, right? That the process thinks it's operating in. So we have to take the virtual page number, these 36 bits, and shove them into the translation look-aside buffer cache to see if we have an entry in the TLB that says for this virtual page number, here's the corresponding physical page number, right? That's what the thing does for us. And so what is the size that they're showing for this thing? Well, they're saying this is the L1 TLB. Actually, it's the L1 data cache TLB, not the L1I cache TLB. And they're saying we have 2 bits on the right of the virtual page number being used as the index into this cache because we have 4 sets. So we need 2 bits. And then all the bits that are left over, like any cache, are the tag for the entries that are in the cache, right? So why do we have 4 sets? What is the size of the thing? It says right here, we got 64 entries and it's 4-way set associative, right? Well, if you have 64 entries and each set has 4, then you got 16 sets, right? So that's why you need 4 bits to index into the level 1 data TLB cache, right? Is everybody cool with that? If it were the level 1 cache, you'd have 5 bits being used for the index because it has 128 entries, still four-way set associative. So it would have one more bit if we were pushing that into the L1I TLB cache, right? Okay. In any event, what pops out if we get a hit in this is the physical page number associated with this virtual page number. And you'll notice that that physical page number that pops out is 40 bits. And our physical pages are the same size as our virtual pages, 4K. So we need 12 bits. And it's the same 12 bits that come down here out of the virtual page offset and become the physical page offset into that 4K physical page. And here is the 40-bit physical page number. So you'll notice the total size of the physical address is 52 bits, which is bigger than the virtual, which sounds a little counterintuitive, but it doesn't matter, right? But the reality is, for a given motherboard and a given CPU for that motherboard, we don't even use these 52 bits. So suppose your motherboard said, with this particular variety of processor that's on it, you can support on this motherboard a total of 64 gigabytes of RAM. How many address bits would I need to address 64 gigabytes of RAM? Somebody tell me. Anybody? Well, for a gigabyte, I need 30 bits, right? I want to have 64 gigabytes, so I need how many bits? I need 36 bits, correctamundo. 36 bits, I could address 64 gigabytes. Well, say, okay, that's how much this computer's motherboard supports, or this model of processor they stuck on the thing, right? So how many bits? 36 bits. Well, that's less than the 40, right? So I mean, less than the 52. So really, you don't have even coming out of the CPU and lines going down the motherboard, solder traces. You wouldn't have these 52 physical bits. You'd have far less, right? And you wouldn't even have the 36 to access the 64 because how do we access the RAM? We put a row strobe out and then we put a column strobe out, right? So we don't even need, enough wires for the full 36. Right? So hopefully you're seeing the realities of what the overall architectural design of a 64-bit computer looks like, and then the reality of what you actually physically have on your particular computer, your processor, your motherboard, right? But that's really not a big deal, I mean, if we've got it set up so that it's got 52 bits, we can expand those motherboards for a real long time and keep making processors that actually support more and more of these pins actually coming out the processor that are actually supporting a wider and wider physical address base. Because with 52 bits, that's an awful lot of memory, right? That's probably more memory than physical memory than is in all the computers in the state of Washington, right? Could be supported with that size of a physical address space on one computer, right? So that's going to do us for a while unless things get really, really amazingly cheap to fabricate. So in any event, you see that we got this 48-bit virtual address space, take the 36-bit virtual page number, cram it in the TLB. Hopefully we get a hit. We get a 40-bit physical page number out, and then we add the 12 bits as the offset, and we have our 52-bit thing. Well, what if we miss in the translation look-aside buffer? Well, we got to go to the page tables. They live in physical memory, right? So we take the 36-bit virtual page number and we're going to go into the page table to now get the physical page number associated with that virtual page number because it wasn't cached up for us in the translation look-aside buffer. And we talked about how we couldn't have one big Gonzamundus, one level monster page table because that would take up more memory than we have on the whole computer just for one process's page table. So we have to have these hierarchical page tables to get around that. And we looked at some simple examples playing with two-level hierarchy just to get the principle and the idea down. The real computer uses a four-level hierarchy, right? And that sequence of page tables in that hierarchy lives in memory. Where does it live in memory? Well, it lives in memory pointed to by control register 3. There are all these registers on the computer that control the overall sort of behavior of the computer that aren't visible to user level processes. Remember, we have to have at least two modes in the processor, the kernel mode where all the instructions are available and we can see all these registers like control registers, and then the user mode that the user processes run in where you don't have all the instructions available to you that control the overall behavior of the computer, right? So this is just an example of one of those control registers that the operating system would set when it put your process in execution, saying this process's page tables live in memory at these addresses pointed to by this control register. So remember, the virtual memory environment is a per process concept, right? Every process thinks he has his own big virtual address space pointed to by the contents of his page tables. So the OS set the control register 3 to point into physical memory somewhere where these entries would live that describe the page table for this currently executing process. The first entry here, we take the first 9 bits and we subscript into here, we pick that up, and then when that points to the beginning of another page table, we take these 9 bits, subscript into that, pick that up, and we just go down the hierarchy, right? I know you're thinking, "Oh my god, this looks like an awful lot of memory references going on here to resolve this one virtual address." And that would be true if we had to actually touch all those things. But as it works out, these things live in where? Physical memories, so they're subject to the caching hierarchy of the physical cache, right? L1, L2, L3. So they would tend to get cached up, right? Those memory references that are being made there to walk that sequence of page tables. And the last one, the one that actually pops out the physical page number, right? That's the thing that gets cached up into the TLB, right? So when we finally get one by touching it, it shows up in the TLB now in its hierarchy of caches, right? So if we go to the same virtual page number, we're just hitting in the TLB and we're not having to do this over and over. So there's some reasons why, although this looks horrible and is generating a whole bunch of actual physical memory references, in reality, the way it works out is it because of the caching of different flavors of caching, it isn't going to be that bad in practice, right? Okay. So you'll notice that the first three entries just point to another page table. Well, the size of each of these page tables is one physical page of memory, 4K, right? And we have 9 bits subscripting into that. So we have 512 entries, right? 9 bits. So the size of each of the entries is what? Somebody tell me. I got 4K of physical memory that this page table is living in. I got 9 bits to subscript into that 4K. That would give me one of 512 entries. So the size of each entry is what? We'll divide 512 into 4K. What do you get? 2 to the ninth divided into 2 to the 12th would give you 2 to the hello, 2 to the 3, 8, right? So the size of each entry in this table is what? 8 bytes. Well, that kind of sounds interesting. That's 64 bits, right? So each entry in this table is 64 bits, and the first 3 are all the same. They just point to another page table. The last one's different. So the first 3 all look like this. Each entry is 64 bits big, and the bits in that entry in the page table have these meanings. The bit on the very most right is, you can think of it like the valid bit that you've been looking at. Is it mapped into memory right now, or is it laying out on the disk somewhere? If it's a 1, then it's currently mapped into memory. If it's a 0, it lives out on the disk someplace, right? So the next bit over is the permissions thing. What are the permissions associated with this physical page that I'm pointing at here? Read or write. Can I just read it, or can I write into it? The next one, do I have to be in supervisor mode to touch this page? If I touch it in user mode, does that cause a trap? That's what that bit means, right? And then this is write through or write back. What's the policy being used for entries that are dirtied up in this page table? And in the real computer, it's going to be write back. We're not going to do write throughs because we're avoiding disk IOs as much as humanly possible. And then the CD bit has to do with whether caching is enabled or disabled for the child page table, the one that I'm pointing at, the child page table. So I'm an entry pointing at the next page table down, right? The child page table. Is that page table subject to being cached or not, right? And so you can, the operating system, when it sets up these bits in the page table, can control that behavior of how the hardware would react to that, right? Now, the next one, the reference bit, the access bit. Remember when we talked about the OS, when it manages the page tables, might want to implement has to replace an entry in your page table. It might want to implement a least frequently used or a least recently used or some sort of scheme like that for picking the victim. Well, that's this bit that's getting set every time you read or write that entry in the page table. It flips that access bit on, right? And so then the OS could use that access bit to tell which entries got accessed out of the page table, right? When it was implementing its replacement algorithm, it could use that information, and then it would go flip the bit off, right? So maybe periodically we flip the bit off and then we accumulate whether they get accessed or not. That's a really, the real name for that algorithm is not used recently. But in any event, that's the hardware hook set by the MMU that we could use up in the OS for the implementation of the victim selection algorithm for replacing a page. The Intel processor, as it turns out, actually has an option, at least for the first level of the page table. The one here has an option none of the other ones have. And the option on that is whether or not the page point at is a 4K page of memory or a 4 megabyte page of memory. And in the normal sort of circumstances, it's always going to be the 4K page. And the slight exception to that rule is for some devious purposes up in the OS kernel itself, it has some times where it will use for its own purposes, a 4 meg page rather than a 4K page. But for all your user level process crud, this is always going to be the 4K page. So that's kind of an esoteric thing that you won't really worry about till you get into like 447 or something. You may discuss why the OS would do that for certain things it's doing up there. But in any event, it's only available in that first level of the hierarchy. The next one, this GBit, right, stands for global. Now, remember when we talked about the fact that the top half of the process's virtual address space is actually mapped to the operating system. For every process on the system, that top half of each one of those processes maps to the same place up into the operating system, right? Well, when you context switch from one process to another, you want to flush the translation look-aside buffer because all those mappings of virtual page numbers to physical page numbers are for that process's virtual address space, right? They don't have the same meaning for some other process, right? So you got to flush the TLB entries, but you don't want to flush the entries that have to do with those pages from the top half of the virtual address space that are the same for every process. They just map to the OS. You want those to stay there all day long. So that's how that gets accomplished, is with this global page bit. If the entry in the page table has that bit flipped on, it means it's one of these global entries that's the same for every process, i.e. the ones that point to where the OS lives, right? So that's the bit that accomplishes that, that keeps it from flushing out of the TLB. So then we have the actual physical address of the page pointed to by this entry, right? So if you go back to the picture here, actual that points to the beginning address of the next guy down in the hierarchy. And you pick up an entry and he has 40 bits to point to the next guy. You pick up an entry, he has 40 bits to point to the beginning of the next guy. They're 4K pages, right? And then you pick up the actual physical page number, which is the 40 bits for the physical reference, right? So why is it 40 bits that's pointing to the next page in the hierarchy? Well, what are the size of the pages? They're 4K, right? 12 bits for 4K. What's the size of my physical address? It's 52. So how many bits do I need to reference the start of a page? In other words, the 12 bits that are the offset is always 0 for this address that's right at the start of a 4K page, right? So if you think about all those addresses that point at the beginning of a 4K page in memory, they look like 40 bits and then 12 zeros, right? So I only need 40 bits to point to the beginning of a 4K page in memory. That's why this is 40 bits big, because it points to a physical page of memory. Questions about that? So that's the first 3 levels, right? They all have this, and this XD bit is the execute disable bit. That says you can't execute instructions that live in this page, right? So like all those attacks that you were doing with your buffer bomb, right? Where you were shoving instructions onto the stack and then jumping to them and executing them. What if we flip the execute disable bit on for the memory associated with where the stack lived? You wouldn't be able to do that attack, right? Because you couldn't shove code into the stack and then run code off the stack. You can't have instructions living in that chunk of memory, right? So when we set up the lab to enable you to do those attacks, we had to go in the program that you're playing with and flip that bit off because it normally would have been on. The stack memory would have the execute disable bit flipped on, and that's a feature in the hardware that we're using to prevent that kind of attack. So you could do your lab and experience that kind of attack. The code that we had in the program we gave you, flip that bit off. It's normally on for the stack, right? That bit is available in the latter versions of the 32-bit Intel processors and all of the 64-bit processors. Okay. So that's that trick that you were doing where you shoved code into the stack and then ran it. That's what we call trampoline code. And so to prevent trampoline code, we have the execute disable bit. All right. So any questions about it, what any of these bits mean? So then we get down to the very last one, the fourth one, the one on the right is slightly different, right? If we go back and forth, see things that are a little different, right? And the first one is that PS thing that existed here. Well, that really only exists for the first level. The 2 and the 3, the ones in the middle, that bit doesn't get used. You only get that option on the first one, whether it points to a 4K or a 4 meg page. And for all your user level CRUD, it's always going to be 4K anyway. So that's different. That doesn't exist except at the very first level. So you won't see it showing up in the fourth one there, right? And then this new bit that's in there is the D bit, right? And that stands for dirty, which is means that you wrote something into the page, right? Well, the last one is the one that actually points to the actual physical page in memory. So if you write something at this address in memory, we're going to flip on the dirty bit that tells us that page is dirty. So when we're doing our business about managing the page tables in the OS and picking one to throw out when we need to reuse it, right? Make it point to a different physical page. That tells us we need to write that thing back to the disk because it's dirtied since we brought it in from the disk, right? So that's the dirty bit that the operating system is looking at to tell it that it needs to write that page of physical memory out onto the disk to the page file to save it because we modified its contents since we mapped it into your virtual address space, right? Does everybody see that? And then these 40 bits, rather than pointing at another beginning of another page table, is the actual physical page in memory, the address of the physical page in memory that the overall virtual address is referring to. So that's the thing that we got out of the TLB if we got a hit, right? That physical page base address. So when you touch that fourth level in the hierarchy, if you actually were going through and resolve a virtual reference, it would cache that up into the TLB now. And that entry would pop into here, right? All those 64 bits go boom, pop up into there, right? And now, if you reference that virtual page number again, you'd get a hit in your TLB, right? And since your process isn't going to access a whole bunch of different virtual pages worth of memory for any short period of time, in reality, everything's going to pretty much get cached up that you need as your process executes, right? And then, of course, we context switch to another process. We got to flush the TLB and keep all those global ones that point to the OS, right? And so when you first context switch to the new process, you're not hitting in the TLB. You got compulsory misses going on to warm up the TLB. But as you make some references to virtual memory for that process that's executing, it'll cache up those entries into the TLB and then it'll sit there and it'll run fast, but there'll be a little lag right after the context switch where it's having to hit memory to warm up the TLB, right? Does that make sense? So you see how the computer is behaving, what's causing it to behave the way it does. Questions about that? This is the actual real deal of how the real computer looks and how it's using the page tables and the translation look-aside buffer in translating the virtual addresses to the physical addresses, right? So here's our page table. It's 36 bits, right? So that's 4 times 9 out of our total 48-bit virtual address. And offsets from the control register 3, which was set when we context switched to this process for its page tables, right? Then the 9 bits is the subscript in there, 9 bits there, 9 bits there, following these references to memory, and then it's the actual physical reference, right? So it is possible that in order to translate one virtual address to a physical address, the worst possible thing that could happen would be that we'd have to touch memory 1, 2, 3, 4 times, and then actually touch memory to get the thing that we were after. So it could be 5 touches of memory to translate that one virtual address, right? But that's horrible, right? But why doesn't that happen very often? Because of the translation look-aside buffer and because these things on the first, these tables themselves, right? Where do they live? They live in physical memory and as such are subject to caching up in the L1, L2, L3 hierarchy of physical memory caches, right? So these references to these memory locations, right, themselves are physical memory references that are subject to being cached in the physical memory caches. So even if we did have to go to the page table, the next time we went to the page table, it's perfectly possible that the entry that we were after is, since we bring in 64-byte blocks, right? It's perfectly possible that it's got cached up in physical memory after we touched the one that lived next to it or something, right? The other effect that's going on that is preventing us from doing these 5 physical memory references is that if you look at the sizes of these, right? Each of these points to a 4K page of physical memory. So I got 512 of them. So one pointer over here on the next level up covers how much physical memory? Well, it could cover 512 times 4K or 2 megabytes of physical memory could be covered by one entry there, right? And I go one more level over. I got 512 of those. So 512 times 2 megabytes is 1 gigabyte. So 1 gigabyte of ultimate physical memory could be subsumed by this one entry at that level. Well, how much memory is your whole process going to use? Is not going to be using huge swaths out of your virtual address space at any given point in time, right? So you don't really need hardly any entries over in these over their levels. So you're not going to be going to different entries there, right? Does that make sense? Okay. Now the ones that are getting cached in the TLB are the ones on the right here, right? The ones that actually point to physical memory. That's what's getting cached up in the TLB. That number, that 36-bit number associated with that 40-bit number that came out of the right end of the table, that's the thing that lives in the TLB, that translation, right? These other guys, you don't really need a whole lot of those entries in your page table. And we'll see that when we look after the test on Wednesday, we'll get into this stuff. We'll start looking at it from the point of view of the operating system and the different segments of memory that your process occupies and see what kind of things would it put in there in these tables. How many of them would it really have for a given process, right? How many entries would it need to support showing where the memory for a process lives? So there's a number of reasons, in other words, that this horrible 5 touches of physical memory doesn't happen very often at all, right? While the process is gonna be executing. Okay? Now another cool thing that's going on is if you look at the virtual page offset, it's the exact same size as the physical page offset, and that's on purpose, right? So these 12 bits out of the virtual address just get dropped down and become the rightmost 12 bits of the physical address. We have to wait for the physical page number to show up either by hitting in the TLB or by having gotten it out of the page table, right? But these 12 bits are already available to us even before we know what the physical page number is going to be through hitting the TLB or grabbed out of the page table. That being the case, we can go ahead and take those 12 bits and shove them over into the physical cache address, right? And it just so turns out that what is the size of the caches that I'm going to use in the physical caches? Well, I'm using 64 byte blocks, right? So the rightmost 6 bits is the block offset. The next 6 bits is the cache index because I've got 64 sets of 8-way set associative memory in my 32K L1D cache. So those 6 bits can be used as the cache index into the sets of the physical memory even before I know what the physical page number is, because the physical page number is effectively the tag that's in the cache. But I can go ahead and select the set and drop it down into a buffer inside of the physical cache, right? And then when this shows up, then I can compare the cache tag to see if I actually got a hit in the physical memory. So I can overlap that processing, in other words, and that's what this is trying to explain. That you can take the virtual page number, pump it into the address translation, either hitting the TLB or get it out of the whatever, the page table, right, to get the physical page number. But before you even have that, you can take the virtual page offset and shove it into the cache, the physical memory reference cache, right, and use that cache index to go in there and get the entry out of the set so that the thing is available to check the tags against once it shows up over here. And so that leads to this thing that we say that the thing is virtually indexed because the virtual offset bits are the same as the physical bits. So we can virtually index into the physical cache and physically tagged because we need the physical page number to see what the tag is to see if we got a hit in the physical page cache. Does that make sense? So that's not an accident that that worked out that way, right? That you can take these 12 bits on the right and use them into the L1D and the L1I caches, overlapping that operation with seeing if you got a hit in the TLB, right? And then when it did hit in the TLB, then the tag would be compared to see if you actually got a hit in the physical cache. Is everybody cool with that concept? Virtually indexed, physically tagged, physical cache. So we size the thing appropriately, so that worked out, right? Well, after the test, we're going to start looking at how does the operating system look at the process's virtual address space? What's its view of all this nonsense, right? And how does the virtual address space of a process actually get managed by the operating system, these different regions of virtual memory that the OS thinks of the process as being composed of? And how do those relate to stuffing these entries in these page tables that reflect, where things end up being mapped onto the actual physical memory while the process is running? But we'll worry about that after we do our exam. So, since chapter 3, when we finished chapter 3, we did the first test. Since then, we've done chapters 5, 6, and most of 9 now, right? So that's primarily the kind of stuff you would expect to see on the second test, although there may be some old, stuff on there from chapter 3 days. You remember back in chapter 3, we were doing things like how do you represent floating point? How do you represent in two's complement? What's a for loop look like mapped onto the computer? Those kind of things. What's a struct look like laying in the computer? All those kind of concepts. So now, chapter 5, we started talking about doing some optimizations. You remember those optimizations we were doing? And chapter 6, explaining how the cache, the physical cache on the computer works, and how that informs how we write code to optimize things, and analyzing whether we're effectively hitting in the cache based on the way the loop was structured and all those kind of concepts, right? And then now we're getting into the fact that the process is actually running in virtual address land, and that's in turn getting mapped through these mechanisms onto the physical memory in the computer. So all of those concepts supposed to be hopefully coming together in your head at some point to get a deeper understanding of what does the computer actually look like when it's running, and what is it doing? How is it executing these programs, and what is involved in doing that? Okay. So there is some material in the end of chapter 9 that we have not gotten to at this point. And so we'll be covering that after our test the rest of the week. And so we'll have enough time to cover that, and then we'll have some time to look back and review where all we've been and get ready for the final, and sort of, just review all these concepts one last time, see if we can get it all to fit together into one coherent conception of what the computer actually is. Okay. So if you have your lab today, you can use your lab time effectively to work with your TA, working some of this through maybe some of the sample problems in chapter 9, and make sure you understand how to work those things. Or maybe you could use it to ask questions of your TA about, things related to the homework problems you had from chapter 9 that are due tomorrow. So if you have your lab today, or um, tomorrow even, you can use it for that. If you have it Wednesday, then you could use it for still use it, I guess, for asking questions about the homework, but you could also use it for working sample problems out of the book to prepare for the final next week. So um, the stuff we will cover in the course is chapters 1, 2, 3, 5, 6, 9. So that'll be what's on the final, right? So all those chapters 1, 2, 3, 5, 6, and 9 is what we will have covered. Okay. So test two will primarily have questions from 5, 6, and 9, but there may be an odd question or two from the earlier material just to make sure you went back and nailed down some of the things that you might have been weak on in the first exam. So I have office hours at 2 today, and we can go over any of this stuff and work some sample problems, that kind of thing. If I don't see you at 2, I will see you after the test on Wednesday. So good luck on your exam. If I don't see you before then. Any questions before we go? So the test will become available like real early tomorrow morning, like 5 or something in the morning. It'll be available basically till midnight tomorrow. And so you just pick a 2-hour time slot convenient to you that you want to do. Once you start it, you get 2 hours to finish it. Okay? And then we'll have most all the numbers in the spreadsheet by that point. All right. Well, good luck on your test. See you then, or see you at office hours.